Hello, and welcome to this video in the Metallurgy playlist where we're going to review the fundamentals of physical metallurgy. To start with, let me share the screen so you can see the PowerPoint and work along with that. My name is Girish Kelkar, and I am a welding consultant with my website at welding-consultant.com and operating as WJM Technologies, which stands for Welding and Joining of Materials. In this video, we're going to review fundamentals of metals, alloys, phases, and grains, and how they relate to welding. Physical metallurgy is a study of atomic structure of metals and alloys as they melt, mix, and cool down to room temperature. The important concepts are metals and alloys, phases and grains, size and shape of the grains, and solidification of molten metal. Those are the four topics that we'll briefly cover in this video. Other topics such as phase diagrams, formation of phases based on cooling rate, and heat treatment of metals and alloys will be reviewed in later videos. The idea of this video, as well as of this channel, is to cater to those who have an engineering background but do not have a expertise or training in metallurgy or welding. So these videos will give you a brief introduction to the subject and help you in starting to work on welding issues without having the need for a professional metallurgy degree. Metals and phases. Molten metal is a condition of metal where atoms are moving past each other. So molten metals do not have a structure. They are like a liquid. In fact, that is the definition of a liquid, that the atoms are moving around and do not have a structure. As the heat source is removed and the molten metal cools down, the metal atoms start to form a certain structure based on the size and shape of the atoms. And that structure, where they are in a certain pattern with respect to their neighbors, is called a phase. The smallest unit where all the atoms are in phase is called a grain. So you could have two grains sitting next to each other, both having the same phase, but both slightly misaligned with respect to each other. In this molten metal, I have also shown some impurities. These impurity atoms can be smaller than the primary atom or bigger or the same size. And once the molten metal cools down, these impurity atoms end up in the structure and they can affect material properties. Let's look at what is a pure metal. I have obviously written it in inverted commas, indicating that there is no such thing as a pure metal. When we say pure metal, we imply that the dominant metal is of a certain type. So let's say if you're going to say we have pure copper, what does that mean? That means the component that you have in your hand is primarily made of copper, but obviously it's going to have some level of impurities. These impurities, as I've shown in the schematic on the right, might end up hiding within the structure of these grains or along the grain boundaries. So you can see that the grain 1 or grain 2 over here on the right has a certain alignment of these atoms. Grain 1 has the same alignment, but with respect to the other grain, it is off aligned. So where the location where these two grains come and meet is called the grain boundary. The grain boundary region is a bit more disorganized and tends to hide a lot of the impurities along the grain boundaries, which does affect material properties. To give you an example of what a pure metal sounds like, a pure metal, say copper 101, is 99.99% pure, but still has 5 parts per million oxygen and some other elements. The oxygen is the one which affects these properties, so that's why I've listed it out. Copper 102 is 99.99 with 10% parts per million oxygen. And copper 110 is 99.9 with 0.04% max oxygen. And you can actually buy these alloys with separate designations and separate properties. And that shows you how important it is to truly understand what exactly is the alloy that you're welding. So if somebody says that we are going to be welding copper or titanium, the first question you should ask is, what alloy of titanium or what alloy of copper? And do we have the certs for that? Do we know exactly what we are getting? Okay. So it's keep in mind, it is not practical to make a pure metal. You can make it more and more pure for a cost, but there is no such thing as a pure metal. In reality, oftentimes we are actually dealing with alloys where not only we have we are trying to keep the impurity levels low, but oftentimes we are actually actively adding certain elements to the alloy. So we take the primary metal and intentionally add a certain element or multiple elements to that mix to create different properties. So the alloy distribution so here I'm showing you a schematic on the right. We have one phase over here, which is the primary phase with dominant is the primary metal, the gray color, with some locations of impurities. You can actually have pockets of reaction products inside the grain, and that is eventually leads to precipitation of a certain reaction product within a grain called precipitation hardening. Over here, I'm showing a neighboring grain, which is a combination of the primary metal plus the additive metal, for example. And the structure of the adjacent grain can be very different. So you can have two grains which are sitting right next to each other, and they can have different phases and different structures. So properties of these alloys depend on the amount and distribution of these elements. So what is the property of the alloy? That depends on how much is the alloying element, where it is located, and on cooling, how does it form its own phases, or is it distributed at the grain boundaries, or is it part of the reaction products? So all of that decides the properties of that particular alloy. And that is something you will need to know if you want to go dig that deep. The grains I'm showing you over here obviously are in schematic form. In reality, the grain size and shape can be dependent on how these metals actually solidified from the molten condition. In some cases, the grains will be equiax. That means the grains will have the same size and structure in all directions. Usually the properties of these materials are also same in all directions. Oftentimes the grains can be elongated. That means the grains are longer in one or two directions, but shorter in the third. And here the properties of these materials are anisotropic. That means the properties are different in different directions. Specific grain structure can be produced with a mix of mechanical deformation and heat treatment. So you can actually take an alloy, roll it in a certain direction, provide it with certain kind of heat treatment, and produce a very unique microstructure that gives it a certain properties. The challenge when it comes to welding is the original grain structure, which you get when you buy these materials from a supplier. And then when you weld it, it is quite possible that the structure is completely lost in the weld. And now within the weld zone, you have a completely different structure with different properties. And that's what makes welding so challenging. Let's look at an example. Here is a butt weld between two rolled structures. How do you know it's a rolled one? You can see the base metal. You can see the grains have lined up in a certain direction. That is a very typical microstructure of rolled metal plates or extruded wires, for example. You will have a directionality to the shape of the grains. However, if you look at the weld itself, you do not see any direction because these are called equiaxed grains. That means majority of the grains in the middle, they look like they do not have a certain preference in growing in a certain direction. So here we have a weld with directional elongated grains and equiax grains in the middle. So even though the chemistry The chemical composition of these two regions is exactly the same. The mechanical behavior of these two regions can be significantly different, or chemical behavior or corrosion, all of those properties can be quite different. You will notice that there is a region over here which is a transition from one type of grain structure to the other. There is a certain level of gradation in there as well. In some situations, it is more obvious, some situations it is not. So I'm going to show you a microstructure on the next slide where it might be a bit more obvious. Here we have made a weld. You can see the cross section. This is a laser weld. The previous weld was a arc weld, TIG weld in particular. Here we have a pulsed weld, a laser weld, which was made in a single pulse. And we have made the cross section, and we notice that the grains in the fusion zone are not uniform. Grains on the outer edges have a certain structure, and grains in the center of the weld have a different structure. And why is that? So what happens is when you make a weld and when you fuse this volume and you turn the laser off, this molten metal starts to cool down. Because the outer edge of the weld is in contact with cold metal, that is where the grains will start forming initial crystals. And these crystals, as they lose heat to the base metal, they keep growing towards the inside. And you can actually see they start looking like shark teeth going inwards. After the grains have grown a certain size, based on the change in chemistry, the internal grains, internal regions may have an equiax structure. So you might have two different structures in the weld. You can have elongated grains on the edges of the weld pointing inwards, and a region in the middle where we have equiax grains. So here again, even within the weld, you can have different properties. You can have different properties in the middle of the weld and different properties on the edge of the weld. So the first and foremost thing you need to understand in welding is oftentimes you're welding alloys, and inside these alloys you have a lot of impurities often, and depending on how you're made the weld, depending on how the heat was provided, and after cutting in the heat off, how the cooling was provided, that we are going to have a unique grain structure, which is what we need to understand first before going too far in analyzing the weld. So this is the first step that you have to take in understanding physical metallurgy, is conduct a cross-section analysis and look for the grain size and distribution in the weld. Okay. Thank you for paying attention. If you are interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking the subscribe button below. Videos on specific topics are in the playlist, including those for resistance welding, arc welding, laser welding, and metallurgy. And I look forward to keeping in touch with you. Thank you for your time and have a good day.